Hello, this is Mrs. Dowell, and I would like to teach you how to derive an equation for a parabola based upon the way the parabola looks. And this is a skill. So there's a couple of things that I need to show you. All of these parabolas are just slight variations of each other. They have been translated. They have been moved up. Maybe they have been stretched, or maybe they have been shrunk, or maybe they have just been slidden, or maybe the vertex has been changed. But there's a couple of valuable pieces of information that we must gather from each one of these parabolas before we can proceed on with writing the equation of the parabola. First, we need to identify the vertex. That needs to be the very first thing, the very first step in our process. And I realize that the graphs are small, but you can take my information here that each tick mark that is noticeable represents 1. Okay? So in other words, this point right here is the point 0, 3. So in this case, our vertex is 0, 3. Okay. In this case, our vertex is 0, 0. In this case, our vertex is 3, 0. In this case, here's our origin right here. This red dot is the origin, and we're down here below the origin. So our vertex in this case represents 0, -3. In this case, our vertex is also 0, -3. In this case, our vertex, 1, 2, 3, -3, 0. Noticing that they're all very similar, the vertices are all very similar. In this case, the vertex is 0, 3. Over here, we have our vertex at the origin again. And right here, our vertex is again at the origin. All right. Now, the reason why this is significant is because for each one of these 9 examples, I am going to use my favorite equation, my favorite form. Y equals ax minus h squared plus k, where h and k represents my vertex, and a tells me about the shape and direction. So that's why I need to try to gather these 3 pieces of information from each one of these pictures. I will say this much. These have been carefully constructed examples, and therefore they are going to be rather easy for you to find as far as the value of A and the value of the vertex. Not every parabola that you're going to work with is going to be that easy. So we have our vertex for each one of these parabolas, and now I would like to focus on the A value. Perhaps you recall me suggesting in the past that when A is positive, your parabola will open up. When A is negative, your parabola will open down. So we have a nice mixture of parabolas that open up and parabolas that open down. In the first example, A would be positive. A is positive, greater than 0. How do I know? My parabola opens up. A is greater than 0. Opens up. A is greater than 0. Here's my first example of where my parabola opens down. That would mean that A is less than 0 or negative. A is greater than 0. A greater than 0. A less than 0. Parabola opens down. A greater than 0. A less than 0. Okay. That means that in my equation over here, I have got to be sure that when I am deriving the equation of that parabola, that I pay extra careful attention to my A value and make sure that it is positive or negative. The next question is, what is the actual value of A? And again, in each one of these cases, as these are carefully constructed examples, I would like to show you how you can quickly look at a graph and tell what the value of A is. Now, in a previous video, I indicated that A represents the rate of change. That only occurs from the vertex to the very next point to the right of it, or to the left of it for that matter, because it is a mirror image. In each one of these, in every one of these 9 examples, the axis of symmetry is x equals 0. In other words, the y axis. So what I would like to do is show you how I am able to figure out what A is equal to by just looking at my vertex and the very next point right after it. In this case, I have gone to the right 1, up 1. That means A is equal to 1. In this case, let's go down here. From the vertex, I have gone to the right 1, and I have gone down 1. So that means that my A value would be -1. So you can just glance at these and see there are some grids where it is easier to see. To the right 1, up 1. To the right 1, up 1. Notice this point. To the right 1, up 1. A is equal to 1. Notice this point. And it doesn't matter really if you're going to go to the left or the right, because again, they are reflections of each other. So if you say, okay, I've gone to the left 1 and up 1, that's fine. You also went to the right 1 and up 1. So to the right 1 unit, up 1 unit. Now that first number will establish A for you. I would like for you to notice that in this example down here, I've gone to the right 1 and down 1. That means A is equal to -1. But in this example, I have gone to the right 1, but I have gone up 2. That means A is 2. In this last and final example, I have gone to the right 1 and then down 2. That means A is equal to 2. Okay. With each of those pieces of information, your A value and your vertex, you are then prepared to go in, fill in the values that you know, and write your equations for each one of these parabolas. This is to the right 1, up 1. So A is equal to 1. To the right 1, up 1. A is equal to 1. Okay, so I'll write the example for this first one. Y equals 1 x minus 0 squared plus 0. Or, quite simply, y is equal to x squared. In this case, my vertex is 0, 3. My A value is positive 1. Y equals 1 x minus 0 squared plus 3. So this is y is equal to x minus 0 squared is simply x squared. X squared times 1 is just x squared plus 3. In this case, my vertex is 3, 0. So I have y is equal to, whoops, I forgot A. Although A is equal to 1, I still want you to be able to see that I'm plugging it in. 1 x minus 3 squared plus 0. So in other words, this parabola becomes y equals x minus 3 squared. Over here, we begin to start dealing with some negatives. Y is equal to negative 1 x minus 0 squared minus 3. So if I clean that up, I have the equation y equals negative x squared minus 3. For this example, y is equal to negative 1 x minus 0 squared plus 3. So this simplifies to y is equal to negative 1 x squared plus 3. I did not have to put that set of parentheses there. Over here in these last two examples, the A value is different. It's 2. Over here, my A value is negative 2. I guess I didn't write that down. Y is equal to 2 x minus 0 squared plus 0. So if I clean that up, that becomes y is equal to 2x squared. And in my last example over here, y is equal to negative 2 x minus 0 squared plus 0. So this is y is equal to negative 2x squared. All right. I would like to also show you an additional thing. What I have graphed here for you is 4 equations. And I've given you the equation, and I've zoomed in on the graph to try to demonstrate to you that you are able to derive what the A value is by looking at the distance or the rate of change from your vertex to the next whole number. Okay. So I want you to notice the scale down here. This is 0, this is 0.5, and this is 1. So let's look at the red graph. And I want for you to notice that from the vertex, I went to the right 1 and then up 1. And that is how I know that my A value is 1. On this blue graph, I've gone to the right 1, but instead I've gone up 2. I've gone to the right 1 and up 2. So you can see that my A value is 2. On the black graph, it's actually off the grid. But you could see that if I had kept going to the right 1 and up 4. And then finally, the last example, to the right 1 and up a half a unit. So these are carefully constructed values and parabolas that enable you to see clearly where the A value is derived from. Now, if each one of those A values was negative, -1, -2, -4, -1/2, each one of these parabolas would be flipped upside down. It is important for you to know that there is another way, an algebraic way, to solve for A if it is not so readily available by just looking at the graph. So again, the test is how far to the right. You always go 1 to the right, and then you examine how far up did you go before you hit the parabola. 1 to the right, and then how far up did you go before you hit the parabola. I hope this has been helpful to you.